Section: Contents. We're here to discuss large language models such as GPT-3/4, PaLM, and Lambda, which have shown remarkable abilities, often emerging spontaneously, in a wide variety of tasks. These tasks range from language and code translation to compositional reasoning and simple arithmetic operations. Interestingly, these tasks are not explicitly programmed into the model's learning objective, which is typically to predict the next token in a sequence. Many researchers have attempted to understand these capabilities and how they arise as training scale, data type, and model size change. It's a difficult task due to the complexity of the data and the wide range of tasks that are studied. Motivated by a desire to understand the factors that give rise to these abilities, we set out to identify the main elements that accelerate their emergence. These elements might include the format and amount of data, model size, pre-training, and prompting style. In order to examine these factors more accurately, we decided to conduct our study in a controlled environment. Our focus was on teaching basic arithmetic to smaller transformer models like NanoGPT and GPT-2, starting from models with 10.6 million parameters and scaling up to 124 million parameters. Our goal was to understand how these models can efficiently learn basic arithmetic operations such as addition, subtraction, multiplication, square root, and sign. This would give us a clearer picture of how these emergent abilities come about. Here are some of the key findings from our research. Data format and sampling are important. For example, when teaching a model addition, the standard format, A3A2A1 plus B3B1B1 equals C3C2C1, isn't ideal. The model is required to calculate the most significant digit of the result first, which depends on all digits of the two numbers being added together. By reversing the results format to A3A2A1 plus B3B1B1 equals C1C2C3, the model can learn a simpler function, which significantly improves the learning process. Balanced sampling of different types of addition, based on the number of carries and digits involved, also enhances learning. We noticed that there's a sudden jump from 0 to 100% accuracy as the size of the training data increases. This may be surprising, but it makes sense when you consider that learning to add n digits from random samples is like completing a low-rank matrix. We also explored the benefits of using chain-of-thought (CUT) data during training. This involves step-by-step operations and intermediate results, which allows the model to learn the individual parts of complex tasks. We found that this type of training data significantly improved learning in terms of both the number of samples needed and the accuracy of the results. This is likely because breaking down the required function into individual parts allows the model to learn a higher dimensional but simpler function map. We further investigated the relationship between arithmetic and text data during training. Since large language models are trained on vast amounts of data scraped from the internet, it's not practical to carefully separate different types of data. We observed how the model's complexity and accuracy changed with the ratio of text to arithmetic data. We found that learning all the arithmetic operations we discussed earlier can improve the performance of each individual task. We also found that showing one arithmetic example improves accuracy significantly, but showing more examples does not lead to significant improvement. This interplay between text and arithmetic and the role of few-shot prompting is an interesting area for further study. Section summary. Large language models like GPT-3/4, PaLM, and Lambda have demonstrated emergent abilities for various tasks without being explicitly trained for them. In this study, we focus on teaching arithmetic to small transformer models and find that data format and sampling methods significantly impact learning efficiency. Additionally, using chain-of-thought data and incorporating a mixture of text and arithmetic data during training further improve learning performance. Section: Related works. In the field of artificial intelligence and machine learning, we find a myriad of works that have sought to explore how to train models to think and reason effectively. The concept of utilizing in-depth reasoning data goes way back, predating even transformer models. Some researchers have used natural language to generate reasoning steps, while others have shown that symbolic reasoning may suffice. The importance of large sample sizes with small numbers, especially for arithmetic tasks, has been highlighted. It has been observed that there is a correlation between the frequency of numbers in the dataset and the performance involving them. Interestingly, we have discovered that transformers can learn to add numbers that were not part of their training. The term chain of thought refers to the enhancement of a model's performance when prompted to produce rationale. This could be achieved by providing the model with enough informative examples as few-shot prompts. The approach of breaking down complex problems into simpler subproblems, called least to most prompting, can help AI models such as GPT-3 solve complex issues. Even simple prompts like, "Let's think step by step," have been found to improve the model's performance significantly on various benchmark datasets. In the arithmetic domain, we concentrate on decoder-only models, which are primarily suitable for text generation and widely employed in language learning models, LLMs. Encoder-decoder models have also been extensively studied, especially concerning learning arithmetic. Some researchers focus on improving the arithmetic abilities of pre-trained LLMs, while others concentrate on the influence of the learned embeddings. When it comes to showing Turing completeness or universal approximation, most findings usually depend on encoder models. Studies have revealed that modifications like relative position encoding can significantly enhance performance. Transformers have shown the ability to learn linear algebra operations with carefully selected encodings. There have also been efforts to explain the limited numerical reasoning capabilities of GPT-2 using mechanistic interpretability techniques. While our focus is on GPT-like models, it's worth mentioning the extensive work done on other sequence-to-sequence models like recurrent neural networks, RNNs. For instance, RNNs have shown the ability to learn how to execute simple programs with for loops, particularly when trained with curriculum learning. Long short-term memory, LSTM, networks have demonstrated improved performance on text-based tasks such as translation when the source sentences are reversed, mirroring our observations in addition. Neural GPUs have been proposed, which have outperformed prior RNNs on binary arithmetic tasks and shown length generalization, meaning they can perform arithmetic on inputs of lengths not seen during training. The concept of universal transformers, UTs, has also been proposed, which use a recurrent transition function to apply recurrence over revisions of the vector representation at each position, as opposed to different positions in the input. On the tasks from earlier studies, UTs have been found to outperform traditional transformers and RNNs. Lastly, in the realm of data-centric AI, there has been a growing interest in enhancing datasets to ensure better performance. A new benchmark has been proposed where the training code is fixed, and the only way to improve performance is to construct new training sets. Other studies have attempted to leverage the model's reasoning ability to generate explanations and use it to solve complex reasoning tasks. Section summary. In the related work section, it is mentioned that previous studies have explored the use of detailed reasoning training data and symbolic reasoning for arithmetic tasks. It is observed that transformers can learn to add numbers that were not seen during training, and prompting the model with step-by-step thinking can achieve competitive accuracy. The section also discusses the use of encoder-decoder models, the impact of learned embeddings, and the improvement of performance through design changes. Additionally, other sequence-to-sequence models like RNNs and neural GPUs have been studied, and the concept of data-centric AI, which focuses on improving datasets for better performance, is introduced. Section: Preliminaries and Experimental Setup. To start, let's outline the specifics of our study and provide a comprehensive view of the setup we have implemented. We'll touch upon the structure of our model and the data organization and sampling methods we've used and evaluated. Our initial focus is on the fundamental arithmetic operation of addition. Specifically, we're looking at adding two numbers, each having up to 3 digits, maximum value of 999. Later on, we'll demonstrate how our results can be expanded to larger numbers. Our goal is to determine whether a model we're calling NanoGPT can learn how to add using training data of various sizes. Surprisingly, this seemingly simple task may present more challenges than one might expect. We start our training using a traditional set of data, which we'll call the plain data format. Here, we present addition problems to NanoGPT in the form: the sum of number A and number B equals number C. Although it sounds simple, this approach does not yield good results as expected. One reason for this could be that the model is not well optimized for generating the most significant digit, the digit with the highest place value in a number, first. A theory we'll call Lemma 1 suggests that in order to generate the most significant digit, the model must process all the digits of the numbers being added. This implies that the model must learn a global algorithm, meaning it must understand the entire addition operation to produce the correct sum. Unlike the traditional digit-by-digit addition humans perform, this requires learning a more intricate function, leading to lower accuracy, a phenomenon we've called attention glitches. In response, we ponder if there's a simpler way for the model to learn addition. Our proposed solution is to guide the model to produce the least significant digit, the digit with the lowest place value in a number, first. This mirrors the way humans usually do addition, starting from the least significant digit and moving to the most significant. In this approach, the model only needs to understand 3 inputs per digit, the corresponding digits of the numbers being added and the carry-on value, either 0 or 1, from the previous digit. This is less complex than the original format, where the model had to process all digits simultaneously. We propose using this reversed format, which starts with the least significant digit and progressively generates the sum. This approach requires the model to learn a local operation for each digit, making the learning function simpler. This idea is supported by another theory we'll call Lemma 2. These theories are evident in our results. When we compare the results of training NanoGPT with the plain format and the reverse format, we see that the accuracy of the plain format stagnates at slightly above 85%, even with 10,000 samples. However, training with the reversed format improves performance significantly. Additionally, fewer training data points are needed to reach good performance with the reverse format, implying that its associated function is less complicated. Particularly noteworthy is a rapid shift in performance with the reverse format between 1,000 and 4,000 samples. During this interval, the model's ability to add two 3-digit numbers swiftly changes from ineffective to perfectly accurate, leading us to question, why does the ability to perform addition appear so suddenly as the number of training examples grows? Section Summary. In this section, the authors describe their experimental setup for training a language model to learn addition. They initially focus on 3-digit addition and train the model on conventional addition data, but find that the model's performance is poor. They propose a reverse format for training the model, where the least significant digit is generated first, and find that this significantly improves performance with fewer training examples. They observe a notable phase transition between 1,000 and 4,000 training examples, where the model rapidly becomes capable of perfectly adding two 3-digit numbers. Section. Connection to low-rank matrix completion. We noticed something really interesting in our previous section, a sudden change in phase that was rather unexpected. Upon further inspection, we found a fascinating link. Learning how to perform an addition operation on n digits from random samples is essentially the same as filling in a rank 2 matrix. This connection gives us a solid explanation for the sudden phase shift we observed. In this section, we're going to delve deeper into this relationship and explain how learning to add can be framed as a problem of low-rank matrix completion, LRMC. Uncovering this link gives us new insights into the phase change we observed. But we didn't stop there. We also uncovered some additional capabilities of transformer models. We found that these models can do more than what traditional LRMC algorithms are capable of. If you think of learning addition from samples as a rank 2 matrix completion, MC problem, you can imagine it involves an n by n matrix, which we'll call M in this matrix. The entry at the ith row and jth column, or M, I, J, corresponds to the result of adding I and J together. This matrix, M, can be broken down into the sum of two rank 1 matrices, n times 1 transpose and 1 times n transpose, where n is a column vector with entries from 1 to n and 1 is a vector of n ones. From this perspective, learning to add from samples is like solving an MC problem where you only see the entries that correspond to those samples. It has been shown that when the underlying matrix is of rank 2 and has no noise, a simple iterative algorithm, you can find this algorithm in the appendix, works optimally. As shown in the figure, a sudden phase transition happens at around the order of n. This is in line with Theorem 2, which states that the exact solution to the MC problem is unique, given that we have seen roughly the order of n samples. This sudden phase change in LRMC is strikingly similar to what we observe in NanoGPT. To study this further, we focused on 2-digit addition, where n equals 100, as shown in the figure. We compared learning to add through NanoGPT with LRMC, creating a training dataset consisting of the matrix's revealed entries in either their original or reverse format. It's important to note here that the training dataset isn't balanced, as the entries that are revealed are randomly and uniformly sampled for the LRMC experiments. The results of the comparison between NanoGPT and LRMC are shown in the figure. Interestingly, both NanoGPT and LRMC demonstrate a similar phase transition at around 1500 samples, where they both start to learn addition almost perfectly. This observation regarding LRMC offers a reason for the rapid emergence of addition in NanoGPT. Section Summary. Learning an addition map from random samples can be seen as completing a rank 2 matrix, which establishes a connection between learning addition and low-rank matrix completion, LRMC. This connection reveals that transformers have enhanced capabilities compared to traditional LRMC algorithms, as demonstrated by their ability to learn addition almost perfectly with a similar phase transition at around 1500 samples. This connection explains the rapid emergence of addition in NanoGPT. Section. NanoGPT generalizes better than matrix completion solutions. Our study reveals that the NanoGPT model we've developed outperforms the traditional low-rank matrix completion, LRMC, approach in certain aspects. LRMC is notably ineffective when faced with matrices with entirely empty rows or columns. On the contrary, NanoGPT displays an enhanced capability to generalize, learning to perform addition even when certain numbers or specific digit positions are deliberately obscured in the training data. We've also noted that reversing the output during training resulted in notable improvements over the LRMC approach in learning addition. However, we believe there's a potential to boost the learning process by enriching the data format. Given that addition is a multi-step procedure, we looked into the concept of including more information about each step, leading us to a strategy we call chain of thought, COT. This COT approach is designed to guide the model in learning addition progressively, with each step building on the last. In the following sections, we analyze the effect of including these intermediate steps on the learning capabilities of smaller models. Our findings reveal a significant improvement in the model's ability to learn addition with fewer samples. In addition, we carefully assess how the amount of information provided for each step affects the performance of the model. To put this into practice, we experimented with training the model on what we've called scratchpad data, a format that includes instructions for each step of the addition process in varying degrees of detail. We investigated two levels of detail in the instructional steps. 1. The simplified scratchpad format, which provides only the sum and carry information for each digit or step. And 2. The detailed scratchpad, which provides a comprehensive, natural language explanation of each step in the addition process. Comparing the performance of models trained with these different levels of detail gives us insights into how detail level impacts the model's ability to learn addition effectively. The results, as shown in the accompanying figure, demonstrate that the model trained with the simplified scratchpad data can achieve 100% accuracy with only 2,000 samples. The model trained with the reverse format, on the other hand, requires more than double the samples to achieve the same accuracy level. Moreover, the model trained with detailed scratchpad data, which includes even more in-depth information, can perform perfect addition with just 1,000 samples. These results suggest that providing more detailed information enables the model to learn addition more efficiently, requiring fewer examples. We hypothesize that this is due to the decomposition of a complex function to be learned into smaller, more manageable components, allowing the model to learn a higher dimensional but simpler function map. However, it's important to note that while the COT-style training improves the efficiency of learning from samples, it may not necessarily be the most token-efficient approach. We discuss this further in a later section. In summary, integrating scratchpad data and breaking down the addition task into steps appears to be a promising strategy to enhance the performance and efficiency of smaller models in learning addition from scratch. Section summary. The NanoGPT model exhibits capabilities beyond traditional matrix completion solutions, as it can generalize even when rows or columns are empty. By incorporating a chain of thought, COT, approach and providing intermediate steps in the training data, the model shows a substantial improvement in learning addition. Training on scratchpad data with varying levels of detail further enhances the model's ability to learn addition efficiently, requiring fewer examples. This approach breaks down the compositional function into individual components, allowing the model to learn a higher dimensional but easier to learn function map. Section. The importance of intermediate step design, subtraction. In this section, we want to emphasize how critical it is to plan out the intermediary steps in a sequential thought process. To illustrate this, we're going to focus on the operation of subtraction and run some tests comparing two distinct versions of a detailed note-taking method for this operation. These tests will help us better understand why it's important to break down the subtraction process into simpler, manageable steps. Subtraction is different from addition in that the result changes based on whether the first number, which we'll call A, is larger than the second number, B, or if it's the other way around. Our first strategy, which we'll call version 1, is to subtract digit by digit starting from the least significant digit, borrowing when needed. This method can lead to mistakes, though, when A is smaller than B. To solve this, we subtract the number in the most significant digit position, times 10 raised to the power of the number of digits in the result minus 1, from the remaining digits in the result. This method is illustrated in case 2 of version 1. The second strategy, which we'll refer to as version 2, is simpler. If A is smaller than B, we just switch their places and find the negative of the result when subtracting the switched numbers. In other words, instead of computing A minus B, we compute negative of B minus A. Our tests indicate that version 2, which requires comparing the two numbers, performs significantly worse than version 1. The primary steps in version 1 require just single-digit subtraction, along with an addition operation in the final step of processing the result. When looking at where version 2 went wrong, we found that most of the errors came from incorrectly identifying which of the two numbers was larger, even though the intermediary steps were done correctly. This finding highlights the importance of simplifying arithmetic operations into easier intermediate steps. Unless specified otherwise, we use version 1 in all detailed note-taking experiments. Section Summary. In this section, the authors emphasize the importance of carefully designing intermediate steps in a chain-of-thought manner for the subtraction task. They compare two different versions of the detailed scratchpad for subtraction and find that breaking down the subtraction task into simpler intermediate steps, as done in version 1, produces more accurate results compared to version 2, which involves comparing two operands. This highlights the significance of decomposing arithmetic operations into simpler intermediate steps. Section. Extending to longer digit addition. In this part of our research, we're expanding our study from 3-digit addition to include addition of numbers with up to 10 digits. Our goal is to determine if the benefits of using reverse and scratchpad formats, which we previously found to be more efficient, continue to be effective when we deal with larger numbers. We start by noting that the phenomena of phase transition, which we have observed in our earlier studies, remain applicable when it comes to adding larger numbers. Additionally, we find that the benefits of using reverse and scratchpad methods become even more noticeable when dealing with greater digit numbers. Moving forward, we analyze the amount of training data needed to learn to add a number with k plus 1 foot digits by refining a model already trained to add k digit numbers. Our findings show that while the quantity of samples required to continue learning to add k plus 1 foot digit numbers stays relatively consistent when using the reverse and scratchpad methods, the conventional method needs increasingly more samples. Next, we revisit an earlier experiment that used NanoGPT and larger digits. The outcomes shown in a diagram demonstrate a behavior similar to what was seen in another figure for 3-digit addition. This implies that our earlier conclusions also apply to longer number sequences. Interestingly, the performance gap between the modified methods, reverse, simplified scratchpad, and detailed scratchpad, and the conventional method becomes even more substantial when dealing with larger digits. While the conventional method requires an increasing amount of training examples to learn larger digit addition, the reverse or scratchpad methods maintain a consistent requirement for training examples. This finding encouraged us to examine the differences between each method in a fine-tuning environment. We asked if a model trained using reverse or scratchpad methods on k-digit addition data would find it easier to learn k plus 1 foot digit addition compared to a model trained using the conventional method. Section Summary. In this section, the authors investigate the efficiency of reverse and scratchpad formats in longer digit addition. They find that the advantages of using these formats become more pronounced as the number of digits increases. Additionally, they observe that the number of training samples required to learn higher digit additions remains consistent for reverse and scratchpad formats, while the plain format requires an increasing number of samples. These findings suggest that models trained on reverse or scratchpad formatted data find it easier to learn longer digit addition compared to models trained with the plain format. Section. Fine-tuning from pre-trained models. Exploring the adaptability of pre-trained models. In this part of our discussion, we take a closer look at the adaptability of transformer models. We are specifically interested in their ability to use their understanding of lower digit additions to learn higher digit additions. Additionally, we examine how different data formats can influence the amount of data needed to grasp these higher digit additions. Understanding the impact of data formats on model tuning. We're going even deeper into understanding how different data formats can influence the model tuning process. Our aim is to identify if training a model in one format can aid in learning addition in a different format and vice versa. Our method involves starting with a model trained on each data format, using 3-digit addition as an example. Afterward, we fine-tune these models, one by one, using different data formats, but this time with 4-digit addition examples. Our findings, as shown in the included figure, are quite interesting. We've noticed that when a model is trained with the same format as the one used for fine-tuning, the learning process is accelerated. To put this in perspective, if we train a model with a plain format, it performs better than one trained with the scratchpad formats. It seems that using the same format throughout the training process offers a level of consistency and familiarity that is advantageous for the model. Additionally, we find it more challenging to fine-tune a model that has been pre-trained on a detailed scratchpad format to work with other formats. This is likely because the model has to forget the specific details of the detailed scratchpad format and adjust to a new one. To illustrate, a model trained with the plain format, which doesn't use alphabet characters in the data, would be unlikely to generate alphabetic outputs. However, a model trained on a detailed scratchpad format, which includes various alphabets, might be prone to generating them. Therefore, changing to a new format would require the model to forget the old format's specific patterns and fully grasp the new format. Our results underscore the importance of maintaining format consistency during the fine-tuning process, as this can affect the efficiency and quality of learning. We will discuss this topic further in the next section, where we will be fine-tuning pre-trained GPT-3 models. Interestingly, we find that fine-tuning with reverse or simplified scratchpad formats actually yields poorer results than using plain formats. For a more detailed discussion of these findings, please see the following section. Section Summary. In this section, the authors investigate the generalization ability of transformer models in learning higher digit additions based on their knowledge of lower digit additions. They also explore how the choice of data format affects the number of samples required for learning. The results show that training a model with the same format as the fine-tuning format leads to faster learning, while fine-tuning a model pre-trained with a detailed scratchpad format on other formats proves to be more challenging. These findings emphasize the importance of format consistency during the fine-tuning process. Section. Teaching arithmetic operations beyond addition. In this section, we are broadening our investigation beyond just the arithmetic operation of addition. We believe that the insights gained from our study of addition, data sampling, and formatting are applicable to a range of arithmetic operations. We have decided to examine various arithmetic tasks, including binary operations such as subtraction and multiplication, and unary operations like sine and square root. Each of these operations presents its own set of challenges and complexities. For instance, the introduction of subtraction brings in the concept of negative numbers. Multiplication, on the other hand, tends to result in much larger outputs, while sine and square root operations involve calculations with decimal numbers, with a precision up to 4 decimal places in our study. However, we want to make it clear that while we've conducted a detailed investigation, it doesn't cover all the essential arithmetic operations or the complete scope of decimal number arithmetic. Our main emphasis is on integer arithmetic for binary operations, and we are only considering a limited number of digits. As for unary operations, we limit ourselves to a certain number of digits after the decimal point. In subsequent sections, we take a deep dive into each arithmetic operation separately, exploring the effect of data formatting and assessing how relevant our findings are to different tasks. We also analyze the results of training on all 5 tasks simultaneously to understand how it may affect the performance of each task individually. Now, in order to broaden our study to arithmetic operations beyond addition, we need to consider additional tasks. Until now, our focus has been on learning different arithmetic operations separately. In this part, we examine the impact of combined training on all 5 arithmetic tasks: addition, subtraction, multiplication, sine, and square root. We compile a single training dataset that includes all tasks and randomize the order of tasks in our training examples. For instance, a random segment of the training data might display a task order such as addition, subtraction, sine, subtraction, multiplication, square root, etc. We are considering 10,000 training examples for each task of addition, subtraction, sine, and square root, and 3,000 for multiplication. The model's performance is assessed after training on our joint dataset in both zero-shot and few-shot settings. We also compare these results with the performance of models that were trained separately on each task's dataset. In the few-shot setting, each task is presented with examples from any of the 5 arithmetic tasks or some prompt texts, followed by specific test queries relevant to the task at hand. Our results show that training on all tasks together significantly enhances zero-shot performance for multiplication and square root tasks, although it slightly reduces the performance for subtraction. On the other hand, few-shot prompting typically shows improved performance. Notably, this performance remains stable, whether the examples provided are from unrelated tasks or are task-specific. We attribute this consistency to our randomized task order during training, which exposes the model to many instances where one task directly follows another, thus simulating few-shot prompting with different tasks. Additionally, we notice that text prompting performs similarly to zero-shot. We think this could be because the training data does not include text data and the model has never encountered text. Therefore, text prompting acts as a random prefix attached to our test query. Section Summary. In this section, the authors expand their study beyond addition to include other arithmetic operations such as subtraction, multiplication, sine, and square root. They analyze the challenges and intricacies of each operation, considering factors like negative numbers, longer outputs, and floating point precision. The authors also investigate the impact of jointly training on all 5 arithmetic tasks and find that it significantly enhances zero-shot performance for multiplication and square root, while slightly reducing performance for subtraction. Few-shot prompting shows improved performance, regardless of whether the examples provided are from unrelated tasks or task-specific. Section. Mixing Shakespeare with arithmetic data. In this section, we shift our focus from models trained solely on arithmetic tasks to large language models that typically learn from a mix of numerical and textual data. To analyze how such a combination impacts learning, we incorporate both numerical addition samples and textual content into our training set. We then use several few-shot prompts to assess the model's ability to identify the correct context. Our experiment involves a dataset combining numerical and Shakespearean text data. It comprises over 1 million text tokens from the works of Shakespeare, 10,000 simple addition examples, with a total of 120,027 tokens, and 3,000 more complex addition examples in a detailed, scratchpad format, totaling 813,510 tokens. We keep the number of simple and complex addition examples constant at 3,000 and 10,000 respectively, but we vary the mix in our training. We divide the Shakespeare text into segments and insert random numbers of addition problems between them. Our tokenizer works at the character level, using a vocabulary of 80 items, which includes letters, numbers, and certain symbols like plus, equals, and n. We then use a few-shot prompting strategy, providing a small number of examples, 1, 2, or 3, relevant to the task at hand. The aim is to prime the model to generate the type of output we're looking for. We use simple addition prompts for testing simple addition problems, and complex, scratchpad, prompts for the more complex problems. We also try introducing textual content before posing the addition problem, a text prompt. We calculate average performance for each type of prompt and also note the standard deviation for each set of results. The term, few-shot, here refers to the average results of all the 1, 2, and 3-shot prompting trials. Our results show that few-shot prompting can significantly enhance performance, with simple addition tasks performing nearly flawlessly with a training set of 40,000 samples. Interestingly, the model continues to perform well on addition even when we introduce a text prompt, as long as we provide a substantial number of addition examples. We believe this is because in our mixed dataset, addition examples are scattered among the Shakespeare text. As we add more addition examples, there are more instances of addition problems following directly on from the text, which reduces any confusion when text is present in addition test queries. To further investigate the influence of the textual content in our training data, we train a model exclusively on simple addition tasks, but with an expanded vocabulary that includes letters as well as numbers and symbols. We also introduce a variant on our few-shot prompting strategy called noisy prompting, where we give the model incorrect addition examples to work from, i.e., a plus b equals c, where c does not equal a plus b. Our results show that few-shot prompting improves performance even when the model only trains on a single type of task, simple addition. Interestingly, even with noisy prompting, the model's performance remains nearly identical to the traditional few-shot prompting, as long as we give the problem in the a plus b equals c format. However, we find that text prompts can hurt performance when the model trains solely on addition tasks. This supports our earlier finding that the benefit of text prompts comes from combining text and addition. Data in the training set. Section summary. In this section, the authors discuss their experiment where they combine arithmetic and text data in the training of large language models, LLMs. They evaluate the trained models using various few-shot prompts to determine if the models can effectively identify the correct context. The results show that incorporating both text and addition examples improves performance, even when the model is trained solely on addition tasks. Section. Fine-tuning, scaling, and pretraining in larger models. In this section, we aim to bridge the understanding between our trials with the NanoGPT and its application to larger language models such as GPT-2 and GPT-3. We first evaluate the performance of both NanoGPT and GPT-2 when they are trained from a state of randomness. Our observations underline the enhanced performance that comes with scaling up the model, particularly in instances where it is applied without prior specific training or zero-shot settings. We then delve into the influence of how words are broken down, or tokenized, and the role of pretraining within GPT-2 models. We find that models which have undergone pretraining, along with a consistent method of tokenizing numbers, achieved by introducing spaces, are significantly crucial during the training phase for arithmetic tasks. Based on these insights, we then fine-tune a pretrained GPT-3 model on a variety of arithmetic tasks using different data formats. Regarding token efficiency across different data formats, our data illustrates that a more detailed set of training data results in improved efficiency per sample. Nevertheless, this comparison doesn't take into account the associated costs of training and inference. To address this, we perform a cost analysis using the number of unique tokens used during training. We treat each data sample as a unique set of tokens. The number of unique tokens is then obtained by multiplying the number of samples with the tokens per sample. For example, in a task involving adding two numbers each of 3 digits, the average token count for a single training example is 13 for plain format, 15 for reverse format, 64 for a simplified notepad format, and 281 for a detailed notepad format. This calculation doesn't account for the uniqueness of tokens across different samples. If the first sample is 112 plus 129 equals 241, and the second sample is 112 plus 128 equals 240, we would still consider that the model has seen 26 unique tokens, despite only 2 tokens differing across samples. This method ensures that our cost calculation is aligned with a straightforward implementation of attention, without any additional optimizations. The number of tokens required for prompting and completion in each data format, for example, is shown in a table. Clearly, the detailed notepad method uses significantly more tokens compared to the other methods. Our results suggest that the reverse formatting is the most token-efficient approach. While the detailed notepad training is more sample efficient, it requires a larger number of tokens per sample, both during training and inference. Considering that the inference cost for commercial models is determined by the number of tokens used per inference call, the total of prompting and completion tokens, frequent use of models trained on detailed notepad formats might lead to increased overall costs. Additionally, it's crucial to note that the cost of a single forward pass is cubic in relation to the number of tokens, emphasizing the importance of this consideration. For practical purposes, it's vital to assess both the number of samples required to achieve the desired performance and the actual token demands during training and inference. Section Summary. In this section, the authors compare the performance of NanoGPT and GPT-2 models, highlighting the improved performance achieved with larger model scales. They also explore the impact of tokenization methods and model pretraining in GPT-2 models, finding that pretrained models and consistent tokenization of numbers are crucial for arithmetic tasks. Additionally, they conduct a cost analysis based on the number of unique tokens encountered during training, showing that while detailed scratchpad training is more sample efficient, it requires a larger number of tokens per sample, which may escalate overall costs. Therefore, it is important to consider both the number of samples needed for desired performance and the actual token demands during training and inference for practical usage. Section. Length Generalization. In this section, we share our findings from various experiments aimed at evaluating how well our model can work with numbers of different lengths. To begin, we purposely left out examples with 2-digit numbers from our dataset of 10,000 addition problems. This left us with 7,655 problems that used only 1-digit or 3-digit numbers. After training our model with these problems, we then tested it using a dataset with randomly selected 1, 2, 3, and 4-digit addition problems. Unfortunately, the results, which you can see in the related figure, were not promising. Our model was unable to accurately solve problems with 2 or 4 digits. This suggests that in order to perform accurate calculations, our model must have exposure to all possible combinations of digit lengths. This lack of generalization to unseen digit lengths is a key shortcoming. We then wanted to see if our model could handle larger numbers, so we trained it on 7-digit addition problems. Once again, we found that our model had a hard time generalizing to a greater number of digits than it had been trained on. For instance, when we tried to have it add 8-digit numbers, it was unsuccessful. The same happened when we trained the model on 10-digit binary numbers. It couldn't handle the addition of 11-digit binary numbers. We also looked at the effect of using a detailed scratchpad format during training. This involves the model being shown all the steps taken to solve a problem, not just the final answer. When the model was trained on addition problems with up to 3 digits, it had difficulty when we then asked it to solve 4-digit problems. It seemed to randomly drop 1 digit from the 4-digit numbers, incorrectly treating them as if they were 3-digit numbers. We've illustrated these issues in the figure provided, where you can see several examples of the errors the model made. These range from cases where we only provided the question to the model, case 1, to situations where we gave it all the steps to solve the problem except the final answer, case 5. The questions we posed to the model are highlighted in light gray, and the answers it generated are highlighted in light green. As you can see, our model struggled to correctly handle larger digit lengths. Section Summary. In this section, the experiments conducted on the NanoGPT model reveal its inability to generalize across different digit lengths. The model struggles with 2-digit and 4-digit additions, indicating the need for exposure to all digit combinations for accurate calculations. Furthermore, the model fails to extrapolate to larger digit lengths, such as 8-digit and 11-digit additions, confirming its limited ability to handle unseen digit combinations. The model's difficulty in accurately managing larger digit lengths is illustrated through detailed error cases. Section. Limitations. Our research did face a few limitations. First, there was the issue of length generalization. We found that our model struggled to predict beyond the number of digits it had been trained on. This challenge has been documented in earlier research as well. In an attempt to overcome this, some researchers have suggested techniques like relative positional encodings. Others believe that models can only handle tasks that exceed their training distribution by blending fine-tuning, prompting, and scratchpad methods. However, it's worth noting that there have been instances of successful length generalization, particularly with models that have over 100 million parameters. The scale of our model and data was another limiting factor. Because we worked on a smaller scale, we were able to carefully examine how individual components affected the model's ability to learn arithmetic. Our model was a GPT type with a decoder-only architecture, and our main focus was character-level tokenization. We did explore scaling up and using byte pair encoding, BPE-based tokenization, but it's not clear whether our findings would hold true for the large language models, LLMs, currently in use. Finally, our study focused on elementary arithmetic. We chose to analyze basic arithmetic operations as it allowed us to isolate and understand the factors that lead to the development of more complex abilities. While prior studies have shown the emergence of complex abilities, we aim to gain a deeper insight into this phenomenon. Section summary. In our experiments, we found that our model was unable to predict numbers beyond the number of digits it was trained on, which aligns with previous research on the challenging task of length generalization. However, there have been cases where length generalization was observed, but only in models with a much larger number of parameters. Additionally, our findings are limited to a smaller scale model and character-level tokenization, so it is uncertain if they can be generalized to larger language models used in practice. Our focus on simple arithmetic operations aims to isolate factors contributing to emergence and provide a deeper understanding of this behavior.